in homology is represented by a holomorphic connected embedded holomorphic curve, then you can take this vector and just take the ray emanating from this point, and then the whole ray will be in the symplectic cone, meaning that every point on this red line is represented by a symplectic form. Okay? Statement clear, Alexei?
So, yes, so we take our homology space, and we take just our symplectic form, and we draw a ray in the direction of point gradual of C.
Right. The red segments are parallel.
Yes, and we like to represent everybody in this array by symplectic representative.
Exactly. All these points. Negative doesn't work. So there are two things to say. You have to emanate positively, and you need that CC is non-negative. Otherwise, it doesn't work. Otherwise, it works for a little bit. But we will need in the proof that we will go essentially to infinity.
Okay.
We need it all the way. Okay?
Okay, Felix.
Okay, so this is inflation lemma. This is what?
Excuse me, Felix, I have made some error. I have started recording not from very beginning. Can we just go back, show me the previous blackboard, just to make everybody everything complete, just for some administrative reasons? Yes. Can we show inflation lemma? Just one more. Inflation lemma.
Ah, the inflation lemma.
Yeah. Okay.
So we have this class.
Yeah. Yes. Yes.
And this is very important.
Yeah, yes.
And then you can deform the given class to this direction for S non-negative, right?
Yes. Okay, thank you very much. I think everything is fine with recording, so it's recorded. So.
Good. But it should anyway not be recorded, no? You told me it's not recorded, but I don't care. From now on, everything will be recorded. If you make laugh, it will be recorded. I tell you, everything. Okay.
Yes. Okay. Okay.
So, okay, let's start the proof. I will only make the proof if CC is 0, but the general proof is similar. Okay, so what do we know? It's very simple construction. It is really, well, in this case, it is extremely simple, as we will see. And in the case it's non-negative, it's similar. So we know that omega restricted to sigma is symplectic, right? Because sigma is holomorphic curve. Sigma is the representative of C, the holomorphic representative of the class C. And then we also know that sigma square is 0, so the normal bundle is trivial, right? So what I have this surface, and now I take a little normal neighborhood that is here just a product. So I have sigma product D. In the general case, it would be a non-trivial product. And then it is really simple. Then, now you take in this disk, you take a bump function, or more precisely, a bump form. You just take a little bump of R1. Right? Well, I call it bump form. It's a function, radial function, dx dy. And I want that it's non-negative and the integral is 1. The integral over the disk is 1. Okay? Come back. And now it's almost done. So, do you see that? So we have this, now we put this f of r dx dy defines us a 2 form on M, because just in this tubal neighborhood, we take everywhere this, and outside we take 0. So this is a 2 form, and it's of course closed, and it's called beta. Okay, so now I go on. So we get the closed two form beta. On the manifold. Okay, and what? And what? And the key is that the class of beta is the Poincaré dual of sigma. Well, of the class of sigma. So this is, you see, with Poincaré duality, with forms, one can really think of it very geometrically, as you can read in bottom 2, and that's how it goes. When you have such a surface sigma in a form manifold, how can you construct a form that represents the Poincaré dual? You just do these bump forms. You just go to the normal bundle, take such f of r dx dy, define beta that way, and it works. Just by the intersection properties, right? This sigma is, when you integrate beta against sigma, you exactly get what you need by construction. So, I mean, in formulas, what is beta of z x y for z in sigma? And for x, y in the disk, it's just f of r dx dy. So the z just does not appear. And if the bundle is not trivial, it's not much harder. You take a connection somewhere, the connection form. Okay. So now now it's done, because now when we take omega plus s beta. So this is closed because omega is closed and beta is closed. So, and I claim that if sigma, if s is at least 0, then this is actually symplectic. And the reason is that you just compute it. It's just a trivial computation. So what is it? I only have to check that the square is positive, right? So omega plus s beta squared is omega squared plus maybe 2s omega beta plus s squared beta squared. Right? But this is positive. When you integrate, you get something positive, and here you get something non-negative, and this is also non-negative. Ah, wait. Oh no, this is actually 0. Because there is no dz, right? So this is positive, and therefore we have symplectic. Okay, so this is a very simple but useful observation.
Wait a second. Is this related to the fact that c squared was 0 rather than...
All right, and in general it's bigger or equal than 0, and at this point you need that c squared is bigger or equal than 0. Because beta squared is c squared, which by assumption is non-negative. In our simple case, 0, but you know, otherwise you need connection form and something, because I just used here global coordinates for the normal bundle of sigma.
Okay.
It's true in the general proof it's a bit harder with connection form, and then this term is like this, and this is kind of key that this is non-negative, and this is anyway already good. So there is a kind of one good reference for all this in a McDuff paper, where it's carefully written out in the general case, but it's not more than half a page. Okay, so now we will use that. Okay, so what is now the main argument in our proof? Yeah, we have what? We want to use the inflation lemma in order to show that our form that corresponds to a big embedding of big poles is, well, that should correspond to that, is represented on the blow up by a symplectic form. This alpha, right? You remember? Big A times L minus sum AJ EJ. And now what we do is, well, first we just embed very tiny balls, epsilon AJ big. This can of course always be done. And then we try to deform the thereby, well, as we already know, thereby constructed symplectic form to make this epsilon 1 using inflation. I will write a bit. Okay, so we now take, we first do a ridiculous embedding. So we take a small epsilon positive. And then, of course, we find an embedding. Into, well, let's say 4. Right, for epsilon small enough, well, just use a Darboux chart and put them. And now we already know that if we have such an embedding, we have a symplectic form by what we saw before. So by this implication that 1 implies 2, we have that this form, I call it alpha epsilon, no, it's a Poincare dual. So this has a symplectic representative. Right, so we take small epsilon, take this small ball embedding, and then we know that to an embedding of symplectic balls in the 4-ball or in CP2 corresponds symplectic form on the blow up. We have not done it in detail, but used it. So what is now our situation? I make a picture of the homology. The homology is of course the one from CP2 generated by the line, and then the new directions given by the exceptional divisors. So somewhat formally, I want to look at this. Here is direction of L, which is the Poincare dual. And here I only look at the direction of one element, namely this. So minus sum AJ EJ. And what do we know? So here is 1, and here epsilon, and here A. And here is alpha epsilon. Right? Can you see it? So this point we have already represented. But what we would like to have is this point, alpha. You see? So what we know is in the symplectic cone is this point. And actually this whole line, but it doesn't really help. But we would like to go here to alpha, right? Alpha 1. So now, of course, the first idea is to do inflation here long, in this direction. That's the first idea, to go along the green line, right? Then we will be done to represent this point. Alpha is the one we want. It's AL minus this. So this we have, but we want to enlarge it. So we want to go up here. Okay, but this doesn't work. So because let's compute, right? For inflation, you need certain things. You need that CC is positive, but okay. So inflating along the green direction does not work. Let's maybe compute it. So a little problem is that inflation along, okay, problem. Inflation along alpha minus alpha epsilon does not work. So this will be the natural thing. And the reason is that the square should be non-negative. Otherwise, as we saw in the proof, maybe I go back. You see, in this proof, we want to go at the end to S to infinity. But then this term becomes important. But if this b square is negative, the positivity from omega is dead. So it's very important that here we have non-negative for CC, which is beta beta. Okay. So let's compute because okay, you immediately well, I leave it as an exercise. Alpha minus alpha epsilon. You have formulas. You can immediately compute it. Squared is minus 1 minus epsilon squared sum aj squared, which is negative. So it does not work. Okay. But what you do is you simply deform somewhere else. So you deform in this direction, and go here. And we will check that you can do that. And then what happens is, can one see? So you see, you want to represent this point. What you prove is that this can be represented. Well, this is not on this point. But then when this point can be represented, then any positive multiple of it is also represented, of course. But when you compute it with scaling, you have to go through the origin. And if you go far out enough, you get very, very close when you do the rescaling. So it's immediate to see that if you can represent all this, then you can get very close to alpha, which is enough for the packing problem. Okay, maybe I should write a bit. Wait a sec. So in the picture, one cannot exactly see it, but so what will happen is we will go about here, and it's good enough. And then when we draw the parallel to this, well, when you read it, you see it. I don't want to make it precise. So this is how it goes. You deform along alpha itself. This vector you already have. This is the omega you take, and you go plus s, the Poincare dual of alpha epsilon. And the whole point is that alpha, what do I want to say? Okay, we want to represent this alpha, but we cannot exactly take him because he's maybe an irrational form, but you approximate it with rational coefficients, and then Saabe-Witten tells you that he can really be represented. Yeah, or here we just have to believe that. But this was the first important application of the Saabe-Witten story, to see that if in CP2, of course, the usual form, you take the Studi Fubini, and then you take blow-ups. And these forms, if coefficients are rational, then you can take multiples so that the form in question is actually integral. And then the Poincare dual of that can be represented by a connected holomorphic surface. That comes from Symplectic. Yeah, well, maybe it doesn't make sense that I write much, no? Maybe the key is the picture. So you deform here, and then you rescale.
Sorry, may I ask, so I think first you approximate alpha by something rational, right?
Exactly.
And then you do all the rest.
Exactly. So
okay.
maybe I write that.
Yeah.
I mean, you see, I mean, this I cannot, when alpha is irrational, there is no chance to represent the Poincare dual with a surface. So when alpha is rational, you first multiply the guy so that he becomes integral. Then you represent him. But since you anyway do rescaling and first go with S to infinity, it will be okay, this rescaling. So maybe I write a bit.
Also, so what you exactly need for Seiberg-Witten to apply?
So, well, here it was the application of a wall crossing formula that proves you that if you are in CP2 and you do blow-ups with rational. Well, probably cannot repeat. It's somewhere in section 4 of the notes. So you take CP2 with weight 1, you do rational. You do a finite number of blow-ups with rational weights. Then, after multiplying the whole thing such that the form you see has integral coefficients, the Poincare dual of that form has a connected holomorphic representative. But this is really harder than the Seiberg-Witten things we have used before that were on these exceptional, like these blow-up exceptional classes. So this was not in the first Seiberg-Witten. This is already Kronheim and Werovka. No, not just Taubes. Taubes didn't have it yet. Okay. Because you have to do wall crossing somewhere. So okay, let's take it in the stomach. I should have a pen. So when you do, right, I have to be careful. So you have this form, you have this AL minus some AJ, EJ. And they are just reals. But now you approximate them slightly too large rationally. So you take very close by in Q. And then I call this new form, this was alpha, I call it alpha Q. And then you take a sufficiently large, so
can you
take it also
a bit up? Sorry. Yeah, right.
Then of course you have, I mean, alpha square is of course positive, right? You have to do the approximation, of course, so well that alpha Q squared is still positive. And then Seiberg-Witten tells you that this alpha Q square Poincare dual has a J curve representative. Okay, and then you look at our alpha epsilon and add large S of this alpha Q. And then when you rescale a lot, this becomes invisible. So they are now all in the symplectic cone. And then you rescale by a suitable, something close to S. And then you get very close to what you want. I mean, well, can I mean, when you write it out, you understand. So there are certain slopes.
Yeah, just divide by S, come on.
Yeah, you don't want to divide by S.
No.
No, because so you see you in the picture before. So what you want is you want to get on this line. You scale such that you drop exactly on this line, and then
is
you
it
get
important?
Yeah, because I want to represent. Because when I am on this line, it means that I am in the space I want and have certain embeddings of certain sizes, and they are not exactly what I want, but super closed. Right, this I don't want to mess up. If it would be just one block, would be okay. But so you scale such that you drop on this line, and if you have started the right way, you actually end even higher. So it's really not important. If you come by only delta close, it doesn't matter because you anyway always take supremum, right? It's enough to get arbitrary close here.
Yeah, but I think you can write explicitly if you want what you.
You could compute it, and it's in my notes, and I don't have it on here. You can write the rescaling parameter out. It's probably something like S minus epsilon sum AI, and then another thing. I don't know. Okay. Yeah, everything is explicit. So I want to say that everything is easy if you have this Seiberg-Witten result. You do this inflation and apply to the correct direction, and things come. So once you have this existence result of holomorphic curves in a desired homology class, and you do this bot2 construction for the Poincare dual, this inverse direction from cohomological condition to existence of symplectic form condition comes out. But it's indeed the third time we use Seiberg-Witten here. It's just the only really strong tool to find that, to say something about the symplectic cone, about those two classes that are represented by symplectic forms. And here it's really very special that we are on the blow up of CP2, right? It's a very special symplectic form manifold. And Seiberg-Witten works very well in only something like CP2, S2 cross S2, their blow-ups, and a few other form manifolds. And in other form manifolds, when B2 plus is at least 2, Seiberg-Witten is horrible because it depends on chambers and everything gets horrible. So it's very important that we are on a very simple space. We had a ball as a target, compactified it to CP2, and these good properties of Seiberg-Witten do not change because B2 plus, which was 1, stays 1 because all the blow-ups give only negative self-intersection parts. Okay, so and now it's essentially done. So the last step is just, well I just write it out. So now everybody's tired. So the last step is that this 3 we had is equivalent to what we wanted. So right, what was it? It is that alpha square is positive, and that alpha is positive on all exceptional classes. Such that what? Okay, so in the equivalence, you know, this corresponds to saying that a square.
So can you raise it? The camera. The camera. Can
cannot
you
read it.
Right.
Can you see it? So this corresponds when you when you write it out. We know the intersection ring, the cohomology ring. So this corresponds now. Shit, nothing works. So this corresponds to a square, at least sum of the HJ. The volume condition. And the other thing, when you this here corresponds exactly to the two Diophantine equations. So I mean, maybe I write it out. Let's see, what is this here? So this says that C1 of the manifold on a given class should be 1. But what was C1? So C1 is, maybe I make sign mistakes, but is what? 3L minus some EJ. And what is E? Well, these numbers in the Diophantine equation, they were for the coefficients of such an E. It's a certain D times L, plus or minus, I've forgotten, the sum of MJ. These D and L's in the Diophantine systems are just the coefficients in the canonical basis for an exceptional sphere, right? Maybe, okay, so the exceptional sphere is written as D times the line, probably minus the sum of the MJ, EJ. And EJ are the classes of the exceptional devices, and these are exceptional classes. Okay, so when you compute this, you get probably 3D EJ, 3D, there's the, probably minus some MJ, and it should be 1. Equals 1, right? And this is the first linear Diophantine equation. Do you see it? So this here is the first equation in the Diophantine system, right? Okay, and the other one is very chaotic. Let's do the other one too. What is E squared equals minus 1 to say that you are an exceptional class? Let's do that too. So it means that DL minus some MJ EJ squared should be 1. Yeah, but this is E squared. Also part badly written.
Like this.
So,
a bit up.
This is our class.
Not enough, sorry.
This is, huh?
Not visible again. A bit right like this, yes. Like a bit up, right. Well, if you can see.
So this is E squared, right? And E squared should be minus 1. Yeah, but what is it? It's D squared minus some MJ squared. Okay, minus 1. And this was the second Diophantine equation. Okay, so we are done. Well, I maybe just repeat. Everything is geometric and elementary once you eat this Simon-Witten business that tells you that certain homology classes are represented by embedded connected holomorphic spheres. And it's really, I mean, for this inflation, you need that it's embedded. Otherwise, you cannot speak of the normal bundle and cannot do the geometric construction. And from Grand theory, you usually do not have a control on embeddedness. Maybe in this dimension with luck from a junction. But Seiberg-Witten always produces you embedded curves because they arise as zero sections of, as a zero set of certain sections of a certain spinor bundle. So this is automatically embedded. So this is a great advantage of Gromov invariants are in general not embedded, but this variation of Gromov invariants, these Gromov-Taubes invariants, they are automatically embedded, which, for instance, here for inflation is important. Fine. So now the last lecture starts with some delay. So it's about the fine structure. Of symplectic rigidity. So with fine structure, I want to say the following. So we have seen Grove-Long squeezing, right? And Grove-Long squeezing says that you cannot do anything. Just identity is already the best if you map into a cylinder. And now we have seen this problem of embedding certain collections of balls into a given ball. And then you have a certain algorithm to find out whether an embedding exists or not. Now, if we restrict to the special case where all little aj are 1, then we have seen this table. So maybe I want to repeat this. So recall that this pk, so this was the supremum. So it was the percentage of volume you can fill by k equal ball when you map into a ball, right? It's the supremum of the volumes of k times the volume of 4 ball divided by the volume of the target. Such that they embed and they have size 1. Okay, so this percentage business. And I want to reorder this. So this is this, okay, I want to express it in terms of capacities to understand the outcome. So what we have seen is the following table. So we had here K, and then 1, 2, 3. No, okay. And then here pk we have seen. So it was 1, 1/2, 3/4, 1, 24 over 20 over 25. Right? Do you remember that? Okay, so I want to rewrite it in terms of capacity, CK. And so you see, yeah.
So in the formula for pk, the first b for 1 should be replaced by b for of a. So
here
on the no, to the right.
Here.
No. Just in the definition of pk, there is some 1 should be replaced by a.
No, but I fix big. I can always scale one of the whole thing. So I take this as a. I take a equal to 1.
Yes.
Because the answer does not matter.
No. I mean that right. the other one should be replaced.
Ah,
yes.
Sorry. A.
Yes.
A. Thank you. Thanks. Okay. So you see, here we fix this one and want to make this as large as we can. Of course, you can also put here a 1 and make this as small as you can and call it big A, right? And the outcome will be exactly the same. So maybe I do that. You can also write here 1, if you can write. 1, and here A. And then you have to write infimum, and here A. Maybe it's wrong now. And here 1. So you want to make this as small as it gets, and then look what you write. Or is it still supremum? No, it's probably still supremum, no? What? The supremum of this quotient? Right, here it's still supremum. Sorry. So this is equivalent, right? It's just a scaling, okay? So now I look at CK, and CK, I want to remember this. I want to remember just this A instead of this quotient. Of course, if you have K given, you know A, you can compute the quotient, and if you have the quotient, you can compute A. I just want to remember, given K1 balls, the smallest A, so that the K1 balls go in. This is kind of called capacity, okay? So this CK is the smallest A such that they embed. Okay, and then there is an explicit relation. You immediately check that that PK is just K over CK squared. It's not important. I just want to reorganize the information in order to generalize it. Okay, and you can immediately, of course, compute the CK. So you get 1, 1, no, 2, 2, 2. We have partly seen them, right? When we have fixed in the very first lecture, we fixed in the target size 1 and tried to fill it with certain triangles or something. And we have seen this 5 over 2. It was probably 2 over 5, but just by convention. And 8 over 3. And this number is interesting, 17 over 6. And here you get root K. Okay. So now I want to understand this sequence of numbers CK. Can one read it?
Felix, excuse me, do I see correctly that CK is equal to 1, 2, 2, 2, 5 to 5 over 2, yes?
Yeah, correct.
Okay, thank you.
Until 4, it's not very interesting. Okay, so I want in a way to understand these numbers. There are certain rational numbers, but only finitely many, and then it's root K. And I just look at the harder problem. And then these numbers will be kind of explained in a better way. Okay? So I now describe this more general problem. Okay, so we look at harder problem of not embedding. I just describe a different problem, and then we will somehow see that it's actually a more general problem. So we don't embed K1 balls into a ball as small as possible, but we embed ellipsoids into a ball as small as possible. So maybe you found it totally stupid to look at ellipsoids, but in symplectic geometry, it was kind of known that they are good objects for several reasons. There are kind of 6 reasons that were known before why ellipsoids are explaining certain things, and we do that here also. So with ellipsoid, I mean the following. So you take a pen that works. So you take an A, at least one, and then I look at the ellipsoid EAB, which is the set of all Z1, Z2 in C2, so that pi Z1 square over A plus pi Z2 square over B is at least is not more than 1. Can one read? Okay, so what is it? You see, it's the standard ellipsoid with standard axis, so that the projection on the x1, y1 plane is a disk of area A, and the projection of the x2, y2 plane is a disk of area B. Okay? Okay, so the projection takes to like this, and the projection 2 goes to, well, so there is a standard form for any sublevel set of a positive definite quadratic form. You can do linear symplectic coordinate changes, and any ellipsoid can be mapped in such a one. It's a standard form for an ellipsoid when you think symplectically. It's an analog of the real situation where it's given by just 4 numbers, but here you need only 2. Okay, so from now on, I need convention. From now on, I assume that that B is 1, because I want to embed an ellipsoid, and I can always scale it, like we scaled before the balls to be size 1, and I take A at least that big. That's my convention. Okay? And then the ellipsoid I look at is this one. And you probably remember what the ball was. The ball was something like a triangle, and now the ball is something like, well, I painted like this. And the ellipsoid looks like this. So here is A, but probably it should be here, it doesn't matter. And here is 1. And the usual moment map maps to such a shape. Right? But you can really prove that this ellipsoid, you cannot see?
No.
Okay, I want to say that a bit more precise. Now, this you have now to learn by heart. Sorry. The green line we need. Okay, so the green thing we will really need, but I briefly want to say a bit more what the symplectic ellipsoid is. So it's true that in the moment map, I give up with this. You can think of it like this. Oh, hell.
Yeah, maybe some vodka can help.
What?
Some vodka inside. No,
Vodka.
I don't know. Not sure.
To resolve it, good idea. Right, but we only have grappa here. Okay, so looks like this. Here is 1 and here is A, right? And so this is the usual moment map picture, but what I want to say is that, so this E1A is really by something we have almost done in the first lecture, is really this open cross cube. Open. here everything is open. So this is true. It's exactly symplectomorphic to that. Okay, so now I look at the harder problem. I look at the number for every A, at least one. I look at the okay, now only okay, C of A, but this is any number at least one, is the smallest A such that E1A goes in. Fine. So, okay, so with STUSA we computed this function. So this is now a function. It's not for every natural number, right? So the answer is like this. Some time ago. So I give you the graph of C of A. Okay, and I'll probably spend 1 hour with the graph. I couldn't prepare it because there was okay. And well, shit. You know what? I show you this. Can you see this graph?
Yes, sort of.
Like this, closer.
No, not all of, yes, we can see most of it, right.
So you see the numbers down there, where it jumps. So
no, the numbers down there we cannot, but
yeah, there is
like
okay,
this, so we almost can. No, well, almost.
Nothing. Well, maybe you can open the file you have.
Right. Some of us can. But
so
you can also open it and somehow put it to the screen, I think, right?
Yeah, but that takes 10 minutes. Yeah, if one would prepare it, one could do it. Maybe I just tell you somehow how it goes, right?
So what is the page number?
Sure.
Which section is it in?
Probably about 11.
11.
No,
okay.
No.
10. Must be 10.
Can be 10, yeah. When you search for 10. Fibonacci, you find it. When you go for Fibonacci. So what happens? I mean, the point is, so what do we have? We have this embedding problem, right? 1A. A is given, and you want to embed it into a ball as small as it gets.
65.
Did you find it?
Mm-hmm.
Great. So here we want to make this number that we call C of A for every A, at least one, as small as it gets. And we start here at 1. And there is, of course, the volume constraint. It's root A. Because the volume here is A over 2, and here it's this squared over 2. So, of course, the graph must be above this square root, which is not so nicely painted. So the point is that until a certain value, that is called down to the 4, the answer is a staircase. It looks like this. Something like this. And they become finer and finer. And there are infinitely many. I mean, what I want to say is that, so Gromov tells you that nothing can be done. And then you have this finite collection of numbers before. So here you have a kind of well-organized answer in terms of certain numbers I will tell you, and the outcome is an infinite staircase until a certain value, namely golden ratio to the 4. So here you have some staircases that give you obstructions. There are more obstructions than the volume constraint, these staircases, right? And then until another number, probably 7 plus 1 over 9, there are finitely many constraints, and then there are no constraints. So there are exactly 3 parts. Here is a kind of a quite rigid part that is well organized. I will describe it. So then there is a zone of transition between rigid and flexible, which is a bit, something happens, but you don't know why. There are 7 constraint steps. And then you have complete flexibility. So the answer from here on to infinity looks exactly as if you were looking at volume preserving embeddings. There is no rigidity at all. Okay? Of course, this looks a little bit like here. For K balls, we have seen that before, right? For K at least 8, at least 9, there was no, you could fully fill. And before you could not fully fill, and there was sometimes rigid, sometimes flexible. For 4 balls and 1 ball, you could fully fill. For 2 and 3 and 5 and 6 and 7 and 8, not. There were obstructions. Okay? Good. Now, maybe instead of giving the precise numerology of this staircase, which is in terms of odd index Fibonacci numbers, I just want to describe one relation between the 2 problems, because this ellipsoid problem is really a generalization of this problem here. So the fact is that, discovered by McDuff, is that so the ellipsoid, when you specialize to K, so I take an A that by chance happens to be an integer, right? So this embeds into a ball. If and only if this disjoint unit embeds.
No, not visible, sorry.
Thanks for telling.
Right.
Well, maybe I give up and don't use that, but okay. So let's try to understand that. Okay, you learn this green stuff now by heart, okay? Ciao. So let's see that we understand that, right? So what I want to say is that the embedding of K equal ball is the same problem as embedding an ellipsoid of size 1K, but if K is not a natural number, this problem is more general. So it means that on this graph I made before, if we go to integral values, you must detect what we saw before. And that's also true. Question?
So sorry, it's an equivalence. It's not clearly visible.
It's an
arrow, right?
So it's really the same problem. So let's try to see a bit why this is so. So let's for instance see for K equal to 2. So one problem is to embed this into ball, and the other problem is to embed this.
Микрофон это выбор стоит.
Okay. So one direction is easy because an ellipsoid can be cut into two balls, namely like this. You see, this is of course, this is a ball, and this actually is also a ball. You may not believe it, but you should not do this. So up to now, I always wanted to construct things by hand and not write down moment maps. But if you think of a ball as a triangle, because it's the image under the moment map, you can pre-compose your embedding with a, well, you know, with a SL2 linear action on the fiber in the torus and in the base. And then this triangle will become like this. You just shear it over. And then, well, you still have to do something about these points because they are not really tori. So something more must be done, but it's all very elementary. And then you see that.
But isn't it about your splitting of a ball as a product of triangle and square?
Yes.
It's exactly the same thing, no?
So, well, okay, let's do the following. You understand that if I have here an embedding phi of the ellipsoid, I want to say that then I can embed the two balls because I can first put them here and then compose. So let's see that we can see that. So this ball, we already know, it's an open triangle cross this square, and here it's also this cross a square. So here we just pull it here. But there is a little trouble. Why can we put this into this? Yeah, you shear, but then here you want to have not this as a fiber, but you want to have a torus. So you have to do something, but it's not difficult. It's very elementary. So I want to say that up to a little reasoning more, when you have this embedding of an ellipsoid, you have the ball embedding because you can put the balls here in. If I would have had 1,4, I could just cut like this. Right? At 1, 2, 3, 4, 5. So if I have an embedding of ellipsoid 1, 5 into a given ball, I also can embed 5 1 balls because I just put them somehow here in. So about this shearing, let's believe it, it's really elementary construction. So it means that after this elementary construction, you know that, you know what, you know this, right? If you can embed the ellipsoid, you can embed these balls because you can put it here and then here. But the other direction is harder and more important here. So the other direction is, it has a kind of a naive idea that cannot be made a proof, and then it also has a real proof. The naive idea is the following. By things we have essentially done, one can prove that if I give you an embedding of 5 balls into a bigger ball, and then also a second such embedding, then the two are symplectically isotopic. You can always move one to the other. So from this, you heuristically may believe that in some sense you can maybe glue the balls together to get an embedding of one ellipsoid, but this can really not be worked out. So the actual proof maybe, so how much time I have? Something like 20 minutes, right? Or Alexei? Alexei has gone home.
One moment.
Yes.
So I believe that since we have started 5 minutes later, yes, then you can you have 15 or maybe 20 minutes. It's okay. Yes.
Okay, 15 minutes. So I have to make a decision. I should either wait. Right, so I should either explain you why you can go the other way around, or I should explain you the precise form of the Fibonacci stairs. And I decide to do the second. I decide to, if you don't oppose 5 to 1, I will explain the Fibonacci stairs.
Maybe you try to say 2 words about why.
Yeah, okay, I can do that.
What is the method you use?
So, Felix, 20 minutes would be okay. So if you just need 20, so let's
okay.
Just...
I will do 3 minutes on that and then the rest on the stairs.
Okay.
Okay, it goes like this. So this McDuff idea. So you try on an ellipsoid, you try in a way to do the same as before. So you try to understand that an ellipsoid embedding can be obtained via blow-ups. But this is not so easy because when you take out a ball, you can collapse the boundary along the Hopf vibration and get a nice two-sphere, right? We have seen that. If you embed, you try now to copy the proof of before. So you want to say that you can embed such an ellipsoid. And then you also do inflation. So you first take a small ellipsoid, and then you maybe have a symplectic form on some blow up, and then you try to do inflation, and then at the end you get a big ellipsoid, something like, you start with a scale. Like here is maybe A1, and instead you take only epsilon, epsilon A. So the first big problem is if you take out the ellipsoid and collapse the boundary, the boundary of the ellipsoid is still very nicely foliated, but it has one singularity, namely here. Maybe here. Wait, it has no here. Okay, you have to compute. You see, it will give a weighted projected space if you take it out. So it will not, what do I want to say? No, okay, let me make an example, then you will understand. No formulas. So, very good. When you have a ball, what is the characteristic foliation on the boundary given by the symplectic form? You have a ball, and the whole boundary is foliated by Hopf circles, right? Now let's take the ellipsoid 1, 2. So it looks like this. And here, what happens is, here you still have a very good foliation. So this goes like in time. When you take the quadratic Hamiltonian that has one level set exactly this ellipsoid boundary, you go in time 1 here, and here you need time 2. And for any other orbit, if it's closed, what do I say? Any other orbit closes up also in time 2. Any other one. They are all disjoint. When you write down the formula, you immediately understand it. E to the I alpha Z1, e to the I beta Z2. You compute the Hamiltonian system. And if the orbit does anything in this direction, well, he only closes up like this one after time 2. And then the time 1 part has also closed up. So every orbit has period 2, but one has period 1. So if you quotient out, kind of like after the flow of time 2, you get for the one guy a singularity. It looks something like a drop, something like a cone singularity. So this is still for an algebraic geometry, it's probably a very good space. It's a something like a CP2 with a singular point, or where locally just a ball. Well, this surface you get from the boundary is a two-dimensional surface with a cone singularity. So the problem is, in such a space, you don't want to do Seiberg-Witten theory in singular space. I certainly don't want, right? And this will happen when you do exactly what you had before. You have an embedding of ellipsoid. You want to translate this embedding problem on the existence problem of a somehow blown up space. But this blown up space is now singular. You would have to work with singular symplectic structures. And I must say that about 3 years ago, Entov and Verbitsky have done such things. Because there is still a good theory of differential forms of mildly singular spaces. At some point you say Hironaka. So something can be done, but it is not necessary, as McDuff understood. She just uses, as already in Fulton's book, or as they do in singularity theory or algebraic geometry, you do the blow up in, you do, when you resolve singularities, you do it kind of in steps. And here you could do something similar. I just make you a picture. So in a way, you have, let's think of in C2 of an ellipsoid. Looks something like this, right? And instead of taking out the ellipsoid and then looking at the boundary, you do it in steps. You first take out this ball. Here is like 1. And then you take out this. And then you are left with this, right? And then you take that out too. You see, the problem was this singularity. But now what you have is something here. But this thing is not singular anymore. When you look at the determinant, the 2 has become a 1, and now it's regular. So instead of taking out the ellipsoid 1, 2, you take out first a ball, and then of size 1, and then a ball of size 1 minus epsilon. And what happens is, you get now a somewhat strange holomorphic object. Before, we got from the collapse here, we got a CP1, right? The exceptional divisor. So now, first, from the first blow up, you get this, but then you blow up again here. And what you get is a chain of 2 intersecting CP1s. You get a CP1 and another CP1. I mean this, and they intersect transversely. So this is somehow a not so bad object. It's a chain of CP1s that intersect transversely. And what McDuff did is she just didn't take out the ellipsoid, but took out such a sequence of balls and gets then not CP1s, but gets a chains of spheres. And the inflation process, looking carefully of how they intersect, can still be done along a chain of CP1s. Though not easily, there were correction papers. So, and then when you instead of taking out an ellipsoid, you take out a sequence of balls, you can repeat essentially what we discussed for a disjoint union of embedded balls. Before, we also had many CP1s, right? But they were disjoint because the blow-ups were done disjointly. But now we will have, well, this is the easiest, the 1, 2, but in general, there are many more. We will get a kind of a chain. And then along this chain of spheres, you repeat the proof. Okay, so yeah. Not much information, but that's kind of the picture. Good. Okay, so then I want to just give you some numbers because they fit so nicely together. I want to describe at least the first part of this staircase in more details because the numerology is somewhat neat. I describe you how you write down the staircase. So there are infinitely many steps. It goes like this. So first you write down the Fibonacci numbers. So, okay. For some reason, you declare f minus 1 to be 1. It's a bit strange, but people do that also in other contexts. So I take 1, 1, this is the one you think, and then 1, and then 2, and then 3, 5, 8, 13. Okay, so these are the Fibonacci numbers you think, and this is kind of Fn. And then, okay, this is F0, and this is F minus 1. And you should not think about it, okay? So now you only take each second. So you take Gn, which happens to be F2n minus 1, and take only each second, namely this 1, and then 1, and then 2, and then 5, and then 13. So the odd index Fibonacci numbers, okay? And then you look at quotients. So I put gamma n to be Gn plus 1 over Gn. So can you see it? You take this quotient. And then you look at them. So I write you the first terms. Maybe. So gamma 0, gamma 1 dada is it's 1, 2, 5 over 2, 13 over 5, and so on. And this sequence of numbers is monotone increasing and goes down to the 2. And tau is golden ratio. Can I see it? Okay, so now the sequence gamma n, I can tell you how you get the stairs. Okay? So you take the volume constraint curve. Maybe a bit deeper. Okay, so then you have your values. Well, gamma 0 is 1, right? And then 2. Okay. Oh, I made a mistake. Sorry, you put that sequence on the axis here. Goes away. Here will be down to the 4. Okay, so now you draw horizontal lines. And so on, right? For horizontal lines until the volume constraint. And then you do the following. So I have to go here, and then I should take this point, and then I should take the line through the origin, through this point and this point, and it will give a step. And when I'm here, I stop. So this segment was not like in the graph, obtained by connecting. I start here, right? This was the point 1, 1. So the origin is actually here. So then I go up through the origin till I hit, and then I go here. So then I take the line through the origin and go here. Then I take the line through the origin and until I hit and go here, and so on. And this you do until here, and then you get this staircase. Do you believe it? This is just the way how you construct the graph. Once I give you the odd index Fibonacci numbers, you have the answer. Okay? So one step, I can draw you one step. Yeah. So a typical step in the staircase looks like this. You have here, so I should declare AN to be Gn plus 1 over Gn squared, and Bn to be Gn plus 2 over Gn plus 1. No, over Gn, sorry. And then you draw here AN. You check that AN is monotone increasing and BN 2, and they are nested. It's always AN, BN, AN plus 1, BN, and so on. So then you get this nesting. And then over here you have the volume constraint. And one step looks like this.
Excuse me, Bn is equal to Gn plus 2 divided by what? What is the denominator?
Gn.
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 Okay, thank you.
So one step for, there is an nth step, which is sitting on the volume constraint. And it looks like this. And it is completely determined by AN, BN, AN plus 1. And of course, these heights you can also compute. They are given by gamma n. And everything comes from the GNs. And that's it.
Excuse me, what is the abscissa of the third line to the right?
Of this?
Yes. What is this? Yes.
AN plus 1.
Okay, AN plus 1. Thank you.
So what happens is this, so you have here, given the Fibonacci number, you have until this value about 6 point something down to the 4, you have the embedding problem ellipsoid into the ball solved. And from this, you read off immediately the first 6 numbers we had before for the equal balls. But the point is, the values are, you see, the breakpoints are more, they are not natural numbers. So the staircase is not much related to natural numbers, but to these Fibonacci quotients. So, and then meanwhile, there have been about 8 such staircases, and each of them is related to some Diophantine systems and some strange number theories like silver ratio or bronze ratio and other not so nice golden ratios. But okay, for now, there are just some 8 9 cases, and not so clear how deep it is. It's somehow related to toricoritis and monotone symplectic manifolds. But okay, there are some, if one would go deeper with embedded contact homology, one would see many other combinatorial kind of slightly algebraic, slightly number theoretic problems that come up in order to compute such things, such embedding problems. For instance, you can look at certain lattice path in the plane, and then capacities can be explained as length of lattice paths that contain at least a certain area. So there are some discrete isoperimetric problems, and kind of many, although there is this Ehrhart theory of counting lattice points, and this was well developed over the rationals. But now at looking at certain irrational ellipsoids, there is something like an irrational Ehrhart theory. And so in a way, these simple embedding questions are related in some way to many other questions, and whether it's deep or not is not very clear, but one has seen many connections. Right. Bye.
Okay, so let us thank the speaker.
Thanks for your patience.
Are there some questions?
I make some light here. Oops, destroyed. No, I have no questions.
Actually, I have a question. May I ask it? Or should I keep it to myself? My question.
You can ask it.
Sorry, it's about triangles. So if we have just a standard CP2 triangle in the moment map picture,
yeah,
and remove 2 of the sides, so what is it? What's left after that? Is it a ball or not?
So what do you remove?
I remove 2 sides.
Okay. So this is the ball, right? This is the ball.
This is the ball, but what happens when we remove 1 side more?
Oh, you remove also this.
Yes.
But
is it something nice or not?
They didn't think about it.
Okay. I thought maybe it's not. Fine.
Well, as I said, you can of course write it down, but
So
whether it's simply
you're sure it's not a ball, right?
I think topologically it's wrong.
It's wrong topologically.
Because of,
yeah, maybe not so clear. Okay.
not so clear. Okay, I would have to think. Okay. Don't know.
Thank you.
Thanks for the question.
Some more questions. So if there are no more questions, let us thank Felix for his excellent course. So Felix, thank you so much.
Yeah, it was a bit chaotic today, sorry.
It's a pity that you didn't come to Moscow, but we would be very glad to see you next time in Russia.
Yeah, I will try. In 3 years when the virus is gone. Okay, was great you were so patient. Have a good weekend.
You too.
Bye.
Bye.
Alexei.
Okay. Can you switch sometimes your Skype on?
Good. In 10 minutes.
Like, yes. Okay.
Let's do that. I drink a tea, and at 10 to 6. Good. Great. Let's do that. Ciao. Till later.